Welcome to our class notes videos over atomic mass 3B9. In this class notes discussion, we'll be taking a look at that decimal number on the periodic table of elements, and our goal is to come away understanding where they get that number and what it means. First of all, before we get into atomic mass, we need to talk about what a relative atomic mass is, because atomic mass is relative. In other words, they had to come up with a whole new scale that they could use to represent masses of atoms, because atoms were incredibly small. And none of the scales that were used at that time for mass would work for atoms, since they are so small. In other words, it would make no sense to give the mass of an atom in grams. Why? Well, to give you an idea, oxygen atom has a mass of 2.6561 times 10 to the minus 23rd grams, which is this number. That is not an easy number to work with. Trying to use that number every time we wanted to talk about the discussion of the mass of an oxygen atom, it would take forever to write the zeros. It's not a very usable number. So another scale was made up. Before we get to the other scale, what was the gram originally based on? Where do they get how much is in a gram? Even though we're not talking about a gram today, in chemistry we do use grams quite often. And a gram is really the mass of water, the amount of water that it would take to fill a cube that is 1 by 1 by 1 centimeters. Or in other words, 1 milliliter of water is said to have a mass of 1 gram when it's at 4 degrees Celsius, because we know as the temperature changes, the density of water changes as well. The SI unit for mass is the kilogram. A gram is 1/1000th of a kilogram. So what's a kilogram defined to be? And again, this isn't anything huge, but this is just something worth talking about now. Well, there was a time where a kilogram was the amount of mass occupying a solid cylinder of platinum. But in 1795, the kilogram was defined to be the mass of 1 liter of water. 1,000th of a liter of water is called a milliliter. So a gram, which is 1,000th of a kilogram, is how much mass of 1 milliliter of water would have. It would make sense that 1,000 milliliters or a liter would be a kilogram. A kilo is 1,000 grams. In 1799, Kilogramme des Archives, I don't even know how to say that. I think it's French. They actually had a standard, a cylinder of platinum and iridium in 1889. So with this cylinder of platinum and iridium, it became the standard of what a kilogram was being compared to. And that remained in place all the way through last year, or 2019. The kilogram was the last of the SI units to be defined by a physical artifact. What they mean by that is they have physically something there that says this is what represents it. By the way, we'll come down here. We'll skip down here real quick. Where does the term gram come from? Gram is actually French, meaning small weight. Kilo means 1,000, so kilogram would be a small weight, 1,000 small weights. I don't know, something like that. What do we mean by the term relative scale? Relative means we're comparing it to something else. So the kilogram was compared to this platinum iridium cylinder. You're comparing something to something else. What do they mean by relative? Well, to give you an idea or an example, if you had $10, some people would say you were broke, especially if we're comparing you to a millionaire. However, if Marion's Piazza was having a pizza sale and they were selling 5 pizzas for $10 and you were starving, you wouldn't say you were broke. You would say you had just enough money to get rid of your hunger. So how much something is in the relative scale, it means we are comparing it to something else. In terms of atoms, what do they compare the mass of atoms to? They had to compare it to something else. they chose the carbon-12 atom as a point of comparison. It's just what they picked. The carbon-12 atom is an isotope of carbon that has 6 protons and 6 neutrons. They picked carbon-12. So they compare everything to carbon-12. They named this unit the atomic mass unit, and they defined the atomic mass unit to be 1/12 the mass of carbon-12. Again, carbon-12 has 6 protons and 6 neutrons. So essentially, 1 AMU is about 1/12 of carbon-12, somewhere between the masses of protons and neutrons, to give you an idea. The unit is abbreviated. Atomic mass unit is often abbreviated by AMUs. You will also see a U used because it's related to what we call the unified mass unit. You'll also hear the word Dalton also used as a unit for things on the atom scale. Very, very tiny things. So again, the atomic mass unit is 1/12 the mass of carbon-12. To give you an idea in terms of grams, it's about 1.66053892 times 10 to the minus 24th grams, and AMU is very, very small. What about the particles in an atom? A proton is about 1.007 AMUs. A neutron, slightly bigger, about 1.008 AMUs. Electrons are ridiculously small. They're 0.000005486 AMUs. So we're comparing things to the size or mass of carbon. That's the scale they chose. In terms of AMUs, hydrogen is 1/12 the size of a carbon atom. About. It's around 1 AMU. The helium atom is about 1/3 the size of carbon. It's 4 AMUs. Magnesium atom is about twice as big as the carbon atom. It's 24.31 AMUs. Germanium is about 7 or 6 times larger. Carbon's atom is 12.01. That's the average mass of the carbon atoms. Germanium's 72.6, 6 times larger. Krypton, 7 times larger. 12 times 7 is around 84. So this is just a comparison. We're comparing everything to the mass of carbon. So where do they get the decimal number then on the periodic table of elements? Where do we get the decimal number? Well, the decimal number is because all of these atoms have different isotopes making them up. Every atom of a particular element isn't exactly the same. They can have different numbers of neutrons. So what is the atomic mass? It's actually the weighted average of the atomic masses of the element. It is an average of the different isotopes. When we say weighted, it means it depends on the abundance of each of those elements. So weighted average dependence on the abundance. In carbon's box, you'll see a 12.01 AMUs listed there. Actually, none of the carbon atoms actually have a mass of 12.01. It is the average mass of the different isotopes of carbon. What were the carbon isotopes? We had carbon-12, we had carbon-13, we had carbon-14. Those were all isotopes of carbon. So all these atoms contribute to that average. It turns out that 98.9% of all carbon atoms are carbon-12, which means when we look at the atomic mass of carbon-12, it should be very close to this particular isotope's mass, which is 12. Why? 98.9% of them are that mass. So this one's going to impact the mass of them more than all the rest. Carbon-13 is about 1.1%, so that's going to have a little impact on the carbon's atomic mass. About 1 in 100 carbon atoms are carbon-13. Carbon-13's mass is 13. So when we look at the 12.01 in carbon's box, the reason it's so close to 12 is because 98.9% of the carbons have that mass. The reason it's slightly more than 12 is 1 out of 100 or so have 13.033 as the mass. So a weighted average depends on how many are there. If it didn't, we would expect all the carbon's average mass to be 13. Why? One of them's 12, one of them's 13, one of them's 14. If they were distributed evenly, where 33% of them were this, 33% of them were 13, 33% of them were 14, we would take 12 plus 13 plus 14 divided by 3, the atomic mass, which is the average mass, it would be 13. Notice carbon 14 wasn't even mentioned in the discussion of factoring into the atomic mass of carbon. That is because it is really, really a rare atom. 0.00000000001% of them are carbon. That's not enough for it to impact the average mass, which we call the atomic mass. The periodic table lists the atomic mass. Why does it list the atomic mass instead of listing the masses of all the isotopes? The answer is because there are too many isotopes. If we actually tried to list the masses of every isotope, the periodic table would be clogged with numbers. We would have to have every one of these numbers in carbon square. Some elements have a ridiculous number of isotopes. You would not want all those numbers in the boxes on the periodic table. And to be honest with you, in virtually all chemistry calculations, we just need the atomic mass, the average masses of the atoms anyway. The masses of each of the isotopes isn't really significant in, by and large, the majority of chemistry calculations. Here's an interesting question though. Why is the mass of carbon 13 13.0033 and carbon 14 is 14.03241? Well, if you remember, the actual particles themselves were not exactly one. So when you add the mass of the particles up, you will find out that the actual atomic mass can be bigger than the mass number. Sometimes it can be less. Take a look at this one. Magnesium number 24. Magnesium 24. It has a mass of 2398. There are 24 particles in the nucleus, 12 protons, and there are 12 neutrons. That should put it above 24. Well, it is not above 24. And this is because when the nucleus formed at the dawn of ages, something called mass defect occurred. We wonder, what is it that holds all those protons and neutrons squeezed together in incredibly small space? It's called the nuclear binding energy. Some of the mass of the particles is converted to energy by Einstein's E equals mc squared. You need a large force to hold that nucleus together and overcome the repelling force of the positive protons. Atoms that did not release a lot of bonding energy as that nucleus formed, well, their masses might still be larger than the mass number if not a lot of that mass defected to energy. That's going to conclude our introduction to atomic mass, and we'll pick up on our next video with looking at how to actually calculate the atomic mass.